Hello, I just wanted to give a bit of an intuitive idea as to what's happening with Euler's method, and hopefully it's going to be sufficient justification. I'm not going to try to do a proof of anything here, but just try to give you some things to think about as to what's happening and why Euler's method works the way that it does. I think noticing what's happening with movement in the x direction isn't so bad. So we're saying here to get to a new x value, we take our current x value and add h to that. So for example, if I take x sub 0 and add h to it, that's going to bump me up to x sub 1. But I like to think of h, like I said earlier, as being more like delta x. And there's a lot of intuitive sense here, where we take a current x value, we add to it some change in x, and that brings me to a new x value, which we call x sub 1 in this case. And I can keep doing that on and on and on until I eventually sort of block step my way to the x value that I want to end up at. What's happening with movement in the y direction is actually quite similar, but it's a little bit more nuanced to see. So for example, we're saying y sub 1 is equal to y sub 0 plus, here we have our differential equation, f. But remember that differential equation, f a function of x and y, is equal to dy dx. So let me call it dy dx. And this, of course, is evaluated at x equals x sub 0, y equals y sub 0, and then times h. But here I'm going to call h delta x. So if I try to think about this in sort of a generic way, we have that y sub 1 is equal to y sub 0 plus, and here dy over dx, that's not really the same as delta y over delta x, but they have, I think, some similar ideas. We think about dy over dx, we think about an infinitesimal small change in y and x. We also think about these as being continuous, whereas delta x and delta y would be more of a discrete mention of those. But if I try to think about this like, and I'll do this in a different color, so you know that I'm getting kind of sketchy with my notation here. If I think about dy over dx as delta y over delta x, and then back to pink, times delta x, we can start to see a little bit of what's happening. Now this is sort of a crude idea of what dy over dx is. This would have to be as delta y and delta x tend to 0, very small changes, incredibly small changes. But we can sort of look at this and notice that it's not too dissimilar than what we said about x, if I think about it in this regards, that the delta x divided by kind of delta x will cancel, and I get that y sub 1 is equal to y sub 0 plus delta y. Now, I had to do some sort of sketchy things to say this, which is why the y values that we're getting, they're really just supposed to be approximations. This is not an exact idea of how I can represent my y value. It's an approximate idea. So we're thinking about taking our current y value and adding something that resembles some small change in y to it to bump me up to this next y value. And so hopefully this helps sort of uncover a bit of mystery with the formula, where things are coming from. This really isn't proper notation to work with, but I do hope that it's sufficient enough to give you a rough sketch or a rough idea as to how Euler's method winds up being somewhat successful in its attempt to approximate a y value to a differential equation. Let me know what ideas you have about this. If you want to discuss this further at all, let me know over on the course discussion board. Thank you for taking a look at this sort of behind-the-scenes footage of Euler's method, and I'm very hopeful to continue this conversation with you. Until then, though, remember, I'm going to see you next time, but to keep learning, keep dreaming, and to always follow your heart.